And hello everyone on YouTube, welcome back to this OpenFoam video. Yes, looks like the sound is on, everything's working. So today we're going to talk about our CHT multi-region form case. So in the last video we have successfully created a UNV file for ourselves, and after using Idea's UNV to foam, we are able to get the mesh out, and of course we can do a split mesh regions by cell zones and override. Okay, and everything is out nicely. Now thing is this, what then do we do to change our boundary conditions? So if we take a look at the zero original file, okay, and I do vi star, I will actually make our what do you call this? I will make all the boundary conditions for every single field we need. But here you can see that we will only have this boundary field. Yeah, we only have this boundary field, which is internal and calculated, calculated and internal field. So what do we have here? Okay, so yeah, we have all of these fields for us, and as you can see, between each case there isn't very much you need to do here. Okay, I'll just keep typing :bw to kind of cycle through the files and close the files as needed. But you can see there's not really a lot you need to do here, because most of the fields will be changing through the change dictionary fields. Okay, so I'll just quit here. And we'll exit. There isn't very much we need to do, so no worries. Okay, the more important thing is well, we have to go through the constant file and the system file. So if we go through the constant file, you'll see here I've already edited what I need to edit. Okay, first of all, of course, is the gravity. Okay, if you're okay with this orientation of gravity, which is in a negative y direction, nothing to change. Otherwise, do go and change it. Yeah, otherwise do go and change it. What then you will need to do is take a look at your region properties. You'll find that there are two fluid regions. One is the tube and the other is the shell. The solid region will be copper, so you'll need to change it accordingly. Okay, next you will need to take a look at, of course, your individual regions. So look at the copper, look at the copper region, because you will be given an empty file or directory. So what I did was to copy over a template file for radiation properties and thermophysical properties. So for solid region is relatively straightforward, and I did this before in the last video. So I just copied over this HG solid thermal, this thermophysical property file, every single thing word for word, copied into this folder. So no changes there. It's relatively easy if you figured it out before, how to put in the copper thermophysical properties. Or you can actually just find a properties of your own. And radiation properties, there's no radiation here because it's a metal. Well, it's like kind of opaque, so you don't have radiation going through everything. Okay, so the more challenging one would be then the shell and the tube. So the shell, for these fluid properties, you will need to copy the fluid properties over. I have it here for diatherm A. You can use water or any other fluid you want. Okay, turbulence properties also, just like what we have been discussing before. Well, in this case, I use a large eddy simulation model. You can of course use other kinds as well. Though technically speaking, this is a hybrid model between RANS and large eddy simulation. So it's not strictly speaking large eddy simulation per se. but under OpenFoam, it's categorized under LES models. Of course, I have all the template files here. I went through those before, so I'll not go through those again. So copy and paste whatever turbulence properties you want here. Likewise for radiation properties. Yeah, so for our case, we don't really need to worry about radiation properties because the temperature is pretty low. If you go upwards of 500 to 700 degrees, you'll need to start worrying about radiation. Okay, so that's where you definitely need to worry about it. So for tube, the idea is the same. You have radiation properties, thermophysical properties, and turbulence properties. All are as what I have discussed before. Okay, the most challenging of all is to edit your system folder. Okay, in here you will have your control dictionary. Okay, so for one, the functions, the function objects, you will need to make sure it is catered to this particular case. That's one thing you need to change. So I kind of just commented it out because I'm not going to use any function objects here. Okay, I'm going to use CHT multi-region foam as well. And you can adjust your time step, your max Coulomb number, and max diffusion number as you see fit to make sure the whole simulation is stable. Won't go through that too much in detail. Decompose parallel dictionary. Well, if you have seen the running CHT multi-region foam in parallel, it was quite straightforward. You just copy this file over. And if you're not sure how to divide your regions out, you can use the Scotch method, and everything here will just be ignored because Scotch method is an automatic way of dividing the region up into 4 parts, so you don't have to think too much about it. FV schemes and FV solutions. Okay, FV schemes and FV solutions here will be empty. Okay, so BW. Okay, so I'm going to quit. Alright, so here there's nothing too much. So we'll need to sort other files out region by region. So for example, in the copper region, we will have all our files here. Change dictionary dict, decompose power dictionary, FV schemes and FV solution. The latter 3 are of course easier to do. So decompose parallel dictionary, same, you have a Scotch method. Then you have FV schemes and FV solutions. Okay, so just copy and paste whatever excuse me, whatever schemes you have for solid regions, you can use that exactly. Don't need to think too much. So right here also you have these solvers. You can adjust them as well. Nothing too fancy there. Okay, nothing too fancy here. Next thing you want to do is to check out your change dictionary, because this is actually one of the most important. They describe your boundary conditions, and for solid regions this is relatively easy. Okay, so we start with an internal field. We give it an initial condition where everything in the copper is uniform at 293 Kelvin. Okay, so by default, every surface over here, you see here a dot star here, means is a wildcard, meaning all boundaries, all surfaces are having this field called zero gradient. Zero gradient means there's no heat being exchanged. It's an adiabatic condition. Okay, if you're not sure how to name your regions or what patches there are, you can go to here in the constant polymesh and you take a look at the boundary file. So let me go again. You go to your constant and whatever region you have, you go to polymesh, look for your boundary file. So once you are here, you will be able to see what are the patches you need to define boundary conditions for. So you have copper N1, copper N2, copper to shell, copper to tube. So I see that actually I want copper N1 and copper N2 to what do you call that? I want them to let me think. Yes, I want them to be wall patches. Yeah, I want them to I want all of these actually to be wall patches, and of course I want what do you call it, these two patches to be you know, the interfacial boundary condition. Okay, so it's a coupled boundary condition. So this is the one you use: compressible, turbulent temperature, coupled baffle mixed, and this will all be the things here. Okay, this is for processor boundary condition, so you don't have to worry too much unless you are doing a multi-region case. Not multi-region, parallel running. So actually, I think I forgot to add in something here. I need to add in an entry for copper N1 and 2 to make sure both of them are wall boundary conditions. So, okay, okay, so I'll need to kind of deal with that later on, but let me just run through the rest of them. So let me put something here to say insert. Hey, wait, no, I don't have to insert wall boundary conditions because this is a solid region. There's no wall functions. There are no wall functions, so that doesn't really matter anyhow. So okay, I made a mistake there. Okay, anyway, so that's it for copper. Copper, as you can see, is very easy because the only boundary conditions you need to worry about are temperature and temperature gradient boundary conditions. No need to worry too much. Now, what's more challenging here is the shell and tube part. Okay, basically FV schemes and FV solutions, you can use the same schemes as before. Okay, so BW this and BW this, quit. Okay, and look at decomposed parallel dictionary. Also, I'll use a Scotch method, decompose into 4 regions. Do remember that if you use four subdomains for one region, you need to use it for all regions, as I explained earlier in my previous videos about CHT multi-region foam in parallel. Okay. Right, so now we are at in the boundary condition for this tube or shell. Was it shell or tube? It's in the shell. So let's go to the shell region, polymesh, and we'll go to boundary. Okay, we'll go to boundary, and you'll see that all of these are the patches you kind of need to define boundary conditions for. Okay, you need to define boundary conditions for. So what do we have here? What do we have here? Curve outer shell, curve inner shell, outer shell curve, shell N1 and shell N2. These are the boundaries I want to prescribe as my walls. Okay, so see all of this here. The curve outer shell, shell N1, shell N2, all of these are walls. Inlet shell curve and outlet shell curved. These are the so-called piping parts. I want to designate them as walls as well. However, the inlet shell and outlet shell, these are supposed to be inlet and outlet patches. So I won't assign a wall boundary condition to them. If not, they'll start behaving as if they have wall functions, which is not physical. Okay. So shell to copper. Shell to copper is over here. This is the part where you have your interface. Okay, and that we need to be mindful of because this is the interface between the fluid region, which is the shell region, and the solid region, which is the copper region. So if you're not sure what are the boundary conditions you need, do have this open at the right hand side, or do have this open on one of your terminals so you can see what you need to edit. So this is my workflow. Okay, then we talk about velocity boundary conditions. So how I designate this here is that by default everything's a no slip boundary condition, meaning to say the velocity at the wall is 0. Okay, processor type boundary condition, we have to make it a processor. And inlet shell boundary condition, I use the flow rate inlet velocity. Okay, I talked about this in my OpenFoam intermediate videos, so do go and watch it. This is very good and very convenient if you want to prescribe volumetric flow rate and you don't want to think about the exact velocity vectors that you need to put inside your inlet and outlet patches. So by default, this will be a plug flow. Plug flow where the velocity profile is uniform, unless of course you want to extrapolate the profile as you see here, which I did not want to. Okay, the value over here is internal field, which means that the initial condition or the initial guess, initial iteration will be this internal field. And what is internal field? Uniform 0, 0, 0. And the outlet shell will be a zero gradient boundary condition. Then I'll let me go skip to pressure, the pressure part. As you can see here, my change dictionary, I'll have internal field at uniform 1 times 10 to the minus 5, and 10 to the 5, 10 to the 5th power, because in buoyant pimple foam, we are more concerned with the PRGH, the pressure without the hydrostatic part. Okay, so that's the one we'll set boundary condition for. Pressure will be calculated by default. Okay, so at all the walls, curve, outer shell, shell N1, shell N2, blah 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 blah, all of this will be fixed flux pressure, which is essentially a zero gradient boundary condition. But because of hydrostatics and compressibility, I mean this model is for compressibility. There may be some density changes here and there, so you need to use this fixed flux pressure instead. So in the inlet, I will use a zero gradient boundary condition, or else it is pretty much a fixed flux pressure. Outlet, I will fix the value of the pressure, and processor boundary, I'll just leave it as that. Okay, this type processor. Okay, so that's how I do the velocity and pressure boundary conditions. Next is temperature. Okay, temperatures are pretty interesting here. I select the internal field of uniform, a uniform internal field, and basically there are a few ways to designate your boundary conditions for the outer parts. Okay, I use this thing called external wall heat flux temperature. And what is this? Well, I guess more on that in the next video, because I'm running out of time. But these parts are, let's say, in your heat exchanger. Okay, this is a more fine mesh of that heat exchanger. You might have parasitic heat loss because these parts of the heat exchanger are actually exposed to air. Of course, you try and cover it with some insulation, but by and large, they will be exposed and you will lose some heat to the environment, or gain some heat. Or gain some heat, excuse me, or gain some heat if you do this. If you gain some heat, then if it's a cryogenic kind of fluid, which your fluid is very sub-zero, you can gain heat from the environment, which you don't want. So to simulate that, this is the boundary condition that I use. But other than that, you use for places I want it to be adiabatic, I use zero gradient. So inlet shell curve, outlet shell curve, all of this I will fix it at zero gradient. Then in the inlet, the boundary condition, I fix the temperature, which is okay. This is the shell part, which I will say is the cooling bits of the temperature. And of course you have the outlet shell, which I will just say is a zero gradient, okay, which is essentially adiabatic in terms of conduction, but more likely, it is the heat is actually being taken out of the system because of advection, meaning to say the fluid carries with it energy and it's going out of the system. Alright, so your shell to copper here will again be this compressible turbulent temperature coupled baffle mixed. So this is a boundary condition to couple the solid and the fluid regions. And again, we have our standard entries here. Now this boundary condition is more interesting, so it'll take time to explain and also tell you more about the syntax. So I'll stop for now, and I'll see you guys in the next video. Bye bye.